All right, so this is 15.7a, video 2. So at the end of the last video, we did a problem very similar to this one. It was the same density function, 6xy. The only difference was they gave us the order that they wanted us to do the integrals in. As a matter of fact, we can scroll back up here and see that it was dy, dx, dz, and they also gave us the bounds. They didn't exactly give us that in this case. We've got enough information to figure it out, but now we have to do a little bit of work. So it says where E, which is that 6xy, lies under the plane z equals 1 plus x plus y and above the region in the xy plane bounded by the curves y equals the square root of x, y equals 0, and x equals 1. So that last part has given us kind of our two-dimensional domain. So if we sketch what that looks like, our two-dimensional domain in the xy plane, because it does say bounded by the curves, above the region in the xy plane bounded by the curves. So y equals the square root of x, looks like that. Y equals 0, that's the x-axis, and x equals 1, which we'll just say is that vertical line right there. So this is the region, we'll see that's 1, in the xy plane. So in order to write our triple integral correctly, we know that, and this is kind of an important concept, by the way, we know that x is going to vary from a value to a value. X is going to go from 0 to 1. Your last or your outer integral needs to be only values, only non-variable. The ones on the interior can have variables in it as long as it leads you to whatever the one is at the end. What do I mean by that? So let's take a look at what this thing kind of looks like three-dimensionally. I'm not going to do the best sketch ever here, but so let's see. In the xy plane, this thing looks like this because that's the square root function out to x equals 1 and then over like that. And then it's beneath this plane, z equals 1 plus x plus y. So I do know that if x and y are 0, the z intercept is going to be at 1. So we'll say that's our z-intercept there at 1. And then out here, because remember this is x is 1 right here, if I plug 1 in for x and 0 in for y, because that would be what would be underneath of the, right here on the xy plane, that's going to be give me a z value of 2. So then that would go up to 2, maybe right about there. And then right here is the point 1, 1. And how do I know that? Well, if x is 1, plug 1 into here, and you're going to get out a 1 for y. So that's the point 1, 1. So if I plug that into here to get my z value, z is now 3. Probably should scale this one down a little bit to make it look more, that's more like maybe my 2. I know I probably did the other one too high, but this one's going to go up even higher and be like 3. So your plane, a little bit tough to draw. Let's see, it's going to be slanted this way, slanted that way, and then in the back there, I guess it's kind of a dotted line that goes in between them. So it's going to be underneath of that, whatever the heck that thing looks like there. This will actually be more curved because it's got to follow the shape of what's underneath of it. Anyway, the idea is this is the plane. This thing up here is the plane z equals 1 plus x plus y. So z is going to vary from the xy plane, which is z equals 0, up to that. So let's see, z is going to go from 0 to 1 plus x plus y. So that's going to be dz. That's going to be my innermost one. And then we're going to put our 6xy in here. The next one, well, the next one could be whatever we want it to be. We can do this as a type 1 or we can do it as a type 2, but it's basically the two-dimensional domain because we got to figure out how x and y are varying. it seems to me that a type 1 would be the easiest here, although you could do it as type 2. A type 1 means that y is going to vary from a function to a function. So it's going to go from 0, which is still a function, up to the square root of x. And then that's going to be dy. And then the last thing is going to be my dx, and x just varies from 0 to 1. And again, you get that from here, 0 to 1. But the whole concept, before we actually do the problem, is that what I wanted you to see is, in the first integral, in the red integral, it's got some kind of a function in terms of both x and y, which is fine, because then when I do the antiderivative with respect to z and I plug that in, it's just going to give me things out of it that have x's and y's. That's fine, because I still have dy and dx left over to take the antiderivative of. Then when I do the next antiderivative, it's going to be with respect to y, but notice that the bounds of the orange one only have functions of x in them, which is good, because my last, in blue, my last integral only can have x's left in it. Otherwise, I've done something wrong, because then I'm going to end up with variables. So hopefully you'll see how this plays out as we go through it. So let's go ahead and take the antiderivative with respect to z first. So we get 6xyz evaluated from 0 to 1 plus x plus y. Don't forget the dy, the dx, the bounds. I know I say that, but a lot of people tend to get lazy when they do these things. Instead of writing everything out, take the extra few seconds. It's not going to be that big of a deal. All right, we'll plug 1 plus x plus y in for z. So we get 6xy 1 plus x plus y. And then if I plug 0 in for z, that zeroes out. And then we're probably going to need to go ahead and distribute. So we get 6xy plus 6x squared y plus 6xy squared dy dx, and my integrals. All right, now we're going to take antiderivative with respect to y. So that's going to be, whoops, that's going to be, let's see, it's going to be y squared, so it'll be 3x y squared plus 3x squared y squared plus 2xy cubed from 0 to the square root of x. Put my dx stuff on there. Okay, plugging the square root of x into each y. A couple of these are going to work out nicely. If I plug the square root of x into the y squared in the first one, that'll be 3x times x, so that's 3x squared, right? Because y squared, plugging the square root of x into y squared is going to give you the square root of x squared, which is just x, so that works out. The next one is going to be 3x squared times another x, so that's 3x cubed. The last one won't be as friendly. That'll be 2x, and then putting the square root of x into the y cubed is going to give me the square root of x cubed, which is really x to the 3/2 power. So I get 2x times x to the 3/2. Multiplying the common bases, x times x to the 3/2 should give me x to the 5/2. Okay, that should be okay. I'll be able to tell in the end since I know what the answer is supposed to be. All right, so now let's take the antiderivative with respect to x. So we get x cubed plus 3/4 x to the 4th plus, that's going to become x to the 7/2. Dividing by 7/2 is multiplying by 2/7, so that should be 4/7. And that should be from 0 to 1. So again, the 0 will zero everything out. So really what I'm going to get here is 1 plus 3/4 plus 4/7. Common denominator is going to have to be 28. So 28/28 plus, what is that, 21 over 28. and then 12 over, no, 16 over 28. Yeah, that's right. So then 28 and 21 is 49, plus 16 is 65 over 28. And that is the correct answer. So that is the mass that is beneath or between that curve that we started with for z and the xy plane. All right, so let's move on. One of the hardest parts about doing this sometimes is figuring out the bounds and which order you have to put everything in. Sometimes it's going to be, do I use a specific method or not? So in number 4 here, we want to find the triple integral over e of x dv. Okay, so we do have an x in there as our row. That's basically our density function. And e is bounded by the paraboloid, which is defined as x equals 4y squared plus 4z squared, and the plane x equals 4. So if you can remember how to do this, let's sketch what this looks like. And a lot of times this helps to determine your bounds. This is where we really kind of need to know how these things work. So a paraboloid basically is a parabola in 2 directions, and then because it's 4y squared and 4z squared, it's going to have a circular base or circular cross sections. So this specific paraboloid is going to open around the x-axis because it's the part that's not squared. So it's going to kind of look something like this. See how well I can draw this. It's going to kind of look something like this, opening around the x-axis. I'll have a circular base. That's pretty good, actually. So that's not so bad. And that plane right there is the vertical plane, x equals 4. So that's what this part is. That's 4. That's the end. Okay, so that's what it looks like in 3 dimensions. What we also need to figure out is, what is the projection going to be in 2 dimensions? Well, let's figure out how we're going to do this first. So it looks like x is going to vary from the from the paraboloid out to x equals 4. So x varies from this, and that's going to be different all along this, all the way out to this flat piece right there. That's how x is going to vary. Well, if that's the case, then we need to figure out what the YZ plane projection looks like. So let's go ahead and sketch the YZ plane. Well, if you were to kind of stand out here, you know, put a person out here, that's a horrible stick figure, we're going to erase that. Put a person out there and stand there, what would it look like if you looked at it from that direction? Well, it's just going to look like a circle. And hopefully you can see that. That's what you're going to see. That's the projection into the YZ plane. So it's just going to be a circle. The circle is going to have a radius of, what is that radius going to be? Radius is going to be 1, I think. Yeah, because if x is 4, if we plug a 4 in here, you get 4 equals 4y squared plus 4z squared, or 1 equals y squared plus z squared. So yes, you'll have a radius of 1. So that's going to help. So the question is, what's the best method? Could this be done in x, y's, and z's? It certainly can. You would just have to be able to solve this equation right here for the top half of the circle and the bottom half of the circle, or the right and left, depending on which way you did. If you did type 1, you'd have to be going in this direction. You'd have to do the top half of the circle and the bottom half of the circle, and then your y value would go from a number to a number. Or instead, we can have the z part vary as z, and we can do the domain of the 2-dimensional projection in polar, because it's circular, which might make this a lot easier to do. So let's see. The x has to be the integral. X is going to vary from 4y squared plus 4z squared to 4. And that is the order if we're going in the positive x direction. And let's see here, our x has to be there, and then that's going to be dx. So now it's the outer two pieces that we want to try and figure out. Instead of using dy dz, but you still could, maybe it would be best to do this in polar, which instead of dy dz in this, dz, we're going to make r dr d theta. Personally, I think that would be the easiest. If you elect to do it with y's and z's, it still works. Okay, well, let's see. Our radius, because we are talking about the entire space of this thing right here. So the radius of this is going to vary from 0 out to 1. So the radius is going to go from 0 to 1. And we'll do r dr because you still have to include an r in there. And then our d theta, which I will do in red, I guess. Well, that's the entire circle. It's going to go all the way around the circle, so that's 0 to 2 pi. Okay, and again, I think that this is probably the easiest way to do it. You may disagree. You may try to do it the other way. It should still all lead to the same thing. But switching this to polar seems easiest to me. All right, so let's go ahead now and work this out. So the first one is going to be the antiderivative with respect to x, which should be 1/2 x squared. And then we still got r. I'll bring the r over. And let's see, we're going to evaluate that. Well, let's see. Do I want to leave this bound right here in terms of y squared and z squared since I'm no longer using them? Probably not. So if you remember, 4y squared plus 4z squared is the same thing as 4 times y squared plus z squared. And in polar coordinates, the x squared plus y squared, or in this case, y squared plus z squared, is r squared. So that is the same as 4r squared. So I'm going to change that to 4r squared since we want everything in terms of r's and thetas at the end, and then 4 is just a constant that stays 4. That doesn't change. All right, so let me go ahead and bring everything else down with it. 0 to 1, 0 to 2 pi, dr d theta. Let's plug in the 4. And remember, we're plugging it in for x. So that's going to give me 16 times 1/2, so that's 8r. In this case, everything's not going to go away. So 8r minus, plugging 4r squared into x is going to give me 16r to the 4th. But 16 times 1/2 is 8. R to the 4th times another r should give me r to the 5th. So double check that just to make sure, but I'm pretty sure that's right. Again, I'll know at the end if I got the right answer. All right. Now, technically, here we can use our nice theorem, our nice Fubini's theorem, which says that if I can separate my variables and I've got all constant bounds, then we can separate the integrals, which we can, because I have no thetas in here. So 0 to 2 pi d theta times the integral from 0 to 1 of 8r minus 8r to the 5th dr. So the antiderivative of d theta is just theta. From 0 to 2 pi is just going to be 2 pi. You will get used to seeing that one. If you need to write it out, please do, but it'll just be theta, 0 to 2 pi, plug in the 2 pi, and that's what you'll get. Let's see. The other one here is going to be antiderivative of 8r is 4r squared minus, let's see, it's going to be 8/6, which is 4/3 r to the 6th. And we'll evaluate that from 0 to 1. So we get 2 pi times. Plugging the 1 in is going to give me 4 minus 4/3. Plugging 0 in zeros it out. So let's see, we are going to get 4 minus 4/3 is going to be, what is that, 12 minus 4, so 8/3. So we're going to get 16 pi-thirds. That is the correct answer. All right, so that's a pretty good problem to look at, and I think that's probably a good place to stop video number 2. We'll come back with one more, and I believe we've got 3 more examples to do. Again, algebraically, they just take a little bit of time, so we'll stop it here.